Good morning to everyone. Myself, Dr.B.Om Prakash, Assistant Professor in the Department of Mechanical Engineering, JNTU College of Engineering, Anantapur. In this lecture, I want to discuss about the basics of refrigeration and air conditioning. What is the basic definition of the refrigeration? Refrigeration is a process to continuous extraction of the heat from the substance and maintains its temperature of the substance below its surroundings. The refrigeration is defined in several ways. Mainly, the heat is flows from the high temperature of the body to low temperature of the body, and the body is maintains always its temperature below its surroundings. We want to know before discussing what are the different types of refrigeration systems or refrigeration methods. We want to know some of the basic terminology regarding the refrigeration and air conditioning. What is the main terminology regarding related to the refrigeration is the refrigeration effect. The refrigeration effect is also we called as the cooling effect. The cooling effect it is defined as the quantity of heat extracted from the cooled body or a space to be cooled in the given time. Mainly, it is the refrigeration effect denoted by the capital letter N, and simply it is taken into consideration as heat extracted from the cold space by the time taken. And the important parameters like specific heat of the water and specific heat of the ice. Before what is the specific heat of the water is it is around the value 4.19 kilojoules per kg Kelvin, and specific heat of the ice is 2.1 kilojoules per kg Kelvin. And the capacity of the refrigeration unit or the unit of the refrigeration, it is the unit of the refrigeration is we simply consider as a ton of refrigeration. The how to the turn of the refrigeration is defined like this. The capacity of the refrigerating machines are expressed by the cooling capacity, mainly in terms of ton of the refrigeration. The standard unit is used for expressing the capacity of the refrigeration machine is ton of refrigeration. How to define one ton of refrigeration is the quantity of the heat absorbed or the refrigeration effect to freeze 1 ton of water into the 1 ton of ice in a duration of for 24 hours at 0 degrees centigrade. This is mainly where depending on the in terms of the how the 1 ton of the ice, how much of the heat is removed or how much of the heat is extracted from the water from 1 ton of the water. How it converts into the 1 ton of ice in the duration of 44 degrees, 44 hours, sorry, 24 hours at 0 degrees centigrade. Here, the one two terms is coming to the picture. What the latent heat and sensible heat. The latent heat and sensible heat, it is well defined. The sensible heat is well defined. That is, the phase of the substance is the remains same, but in the cooling process, the temperature is falls down from high temperature to the low temperature. And in terms of the heating process, the heat value is increases from low temperature value to the high temperature value, but the phase of the substance is remains constant. For example, ice we taken into the consideration of ice at 0 degrees centigrade. At 0 degree centigrade only, the ice is converted into water in terms of the heating process. In terms of the cooling process, the water at 0 degree centigrade, it is we are extract the heat from the water, and at 0 degree centigrade only the water is converted into the ice. That is we taken into consideration as the latent the sensible heat. Coming to the picture as the latent heat, in the latent heat, mainly at a particular temperature, at a constant temperature, the phase changes occurs a particular substance. For example, at 1000 degrees centigrade, sorry, 100 degrees centigrade only, the water is converted into the steam. That is one of the main simple example. So at zero, at 100, sorry, at 100 degrees centigrade only. So from the water at 0 degree centigrade to the 100 degree centigrade, the phase of the water is in the liquid medium only, liquid phase only. But at 100 degrees centigrade, that is the water is converted into the what we call that is the steam. So that it is the proper, the sensible heat and latent heat is the properties of the substance. So that the ice, the latent heat of ice is around 336 kilojoules per kg. As per the definition of the 1 ton of the refrigeration, how we are calculated, that is the latent heat is mainly we are taken into consideration, that is 336 kilojoules of the heat should be extracted from 1 kg of water at 0 degree centigrade to convert it into the ice. That is, we simplify the equation in terms of 24 hours. That is 336 by 24 at 0 degree centigrade. So that finally, in terms of 1 ton of the refrigeration is around the 230 kilojoules per minute. But as per the ASRE, the American Society of the Refrigeration and Air Conditioning, 1 ton of the refrigeration we are taken into consider as the value is 210 kilojoules per kg, and the in terms of the kilowatts is that is 3.5 kilowatts. Next, we are coming to the one important parameter. Always, we are the performance. How do you we are evaluate the refrigeration capacity is in terms of the coefficient of performance. As like the heat engine is performance in terms of efficiency, and heat pump is also in terms of coefficient of performance only. What exactly the coefficient of performance is? It is defined how much of it is the ratio of heat extracted from the substance, or simply the refrigeration effect to the work done. The refrigeration effect to the work done. The refrigeration effect is how much of the cooling effect. The refrigeration effect is nothing but the cooling effect effect is occurs in between the before entering at the entry of the refrigerator evaporator to the exit of the refrigerator, and work done is simply how much of the consumption of the electrical energy or how much of the energy is required to get the our required refrigeration effect. So that refrigeration effect, the coefficient of performance is the value. So that this COP of the refrigerator is always greater than one, and known as the theoretical coefficient of refrigeration. And then the refrigerator is mainly it is the reversible. It is just like the operation is the reverse of the heat engine only. So heat engine is mainly but works based on the Carnot cycle. So the refrigerator is works based on the reversed Carnot cycles. The reversed Carnot cycles, how the main the proper heat is the property of the substance. Heat is the property, so that heat is always flows from high temperature body to the low temperature of the body, and we want to get some work output. We want to get some mechanical energy, so that we place some one of the components that of the heat engine. When the heat flows from the source, that is the high temperature, so high temperature to the low temperature. So the some amount of the heat energy is converted to the useful work, that is simply called as the mechanical energy. And some of the heat energy it is sent to the with the sink, that is that is the, but it is into the atmospheric and atmosphere, or simply to the as per the our what parameters it is sink, and it is just as like a reverse one only. In this reverse Carnot cycle, always heat is flows from low temperature of the body. Heat does not flow as per the Clausius and Kelvin Planck statement. Heat does not flows from low temperature of body to the high temperature body without aid of any external energy. So that always heat is carried or heat is extracted from the low temperature of the body by the consumption, or by some work is required, or some work is done on the system, only it is achieved. So all the things as per the Carnot cycle only. So that is simply considered as the refrigerator. Same thing, a refrigeration process is in the heat pump also. The based on the applications, the cooling to applications, in the cooling applications we are taken into consider as the refrigerator, and some of the heating applications as the heat pump. So that these are the things just we observe here. What exactly the reversed Carnot cycle is occurs from the evaporator and compressor, turbine and condenser. This is from the evaporator at low temperature side. The leaving condition of the evaporator is always in the vapor condition only, or as a theoretical condition we simply consider the saturated vapor condition. This saturated vapor is enters into the compressor. The compressor only here the work required device. So in this compressor the fluid is compressed that takes place, and the pressure and the temperature is increases up to the maximum level, that is the condenser level only. In the condenser itself, the high temperature and high temperature of the vapor refrigerant, it is enters into the condenser, and it is based on the cooling media, either water cooling or air cooling or evaporating cooling system. The phase change is the what the phase of the substance is what changes from vapor to the liquid, and then these high pressure and high temperature of the liquid fluid, liquid media, it is enters into the turbine, so that the turbine blades are rotate and it produce some of the energy. Same energy we are coupled, we are coupled one of the shaft with the compressor, so that it is rotate and it develops some energy. Some amount of the energy we are utilized for running of the compressor, and then it leaves the from the leaving condition of the condenser is at very low pressure and low temperature condition of the liquid refrigerant. This is the low pressure and low temperature of the refrigerant. It is having the condition is it is ready to extract some amount of the heat from the substance, so that we are enters into the evaporator, and cycle is repeats. Just by observing the TS diagram, it is very simple. The 1 to 2 is evaporator, that is what isothermal condition, that is the 1 to 2, the temperature it maintains constant, that is low temperature only. And then 2 to 3 is the isentropic compression process, where the temperature is increases from T2 to T3 value, and in the condenser value some amount of the heat is resected in the condenser, so that just you observe the process 3 to 4, that is the condenser process only, so that here some the entropy is decreases from S3 to S4, and it maintains the temperature, that is T3 is equal to T4, and then it is enters into the turbine, where the temperature is passed down from temperature T4 to the T3, that is T1 is equal to T2. So what we clearly observe here, it is also theoretically it follows the constant entropy process. And these are adiabatic these are mainly the reverse Carnot cycle consists of the four operations. Just now we discussed about all the things, adiabatic and isothermal, the based on TS diagram. Just you simply see the adiabatic, two adiabatic process and two isothermal process. That is any cycle we are expressed any expression with the help of PV and TS diagrams. Just by with the simple PV diagram, just we observe all the things. From 1 to 2 is the adiabatic compression process. In this adiabatic compression process or isentropic process, that is by S1 is equal to S2, but the pressure is increases from T1 to T2, and the temperature is also increases from T1 to T2. And the next operation is the isothermal compression process, where the pressure is increases from P2 to P3 value, and the temperature is maintained as isothermal. Isothermal, that is delta T is equal to 0, so that T2 is equal to T3. That and then T3 to T4, that is the operation, that is adiabatic expansion of the working fluid. The temperature of the working fluid from T2 to T1, that is equal to, or T3 is equal to T2, or T4 is equal to T1. And final the last operation is the isothermal expansion operation. That is the isothermal expansion operation. What happens? The entropy goes on increases from S4 to S1, and these are TS diagram. Just now we discussed about the things, and COP of the values. Just it is based on only our the work consumption is only the compression, and the refrigeration effect is we consider as the evaporator inlet and outlet condition only, so that the heat rejection, the heat is absorbed at low condition, low pressure and low temperature condition, that is Q2 value. Heat rejected is the high heat values, that is Q1. and work done is just a heat rejected to the heat absorbed, that is Q1 minus Q2, and the and the refrigeration cooling effect is always we are mainly focused on low temperature side or heat absorbing side, so that Q2 as consideration, so that the COP of the refrigerator is simply Q2 by Q1 minus of Q2, Q1 minus of Q2, and by consideration of the temperature value, always the refrigerator cooling effect is where low temperature side, so that is T2 value, and the by consideration of instead of the heat values, the temperature value, the expression is T2 by T1 minus T2. So that COP, we have simply defined the COP is it is the ratio of heat absorbed by the work supply work done, or simply heat absorbed, heat in place of work supplied, that is heat rejected minus of heat absorbed. By simple the Q but the heat values, we know the what the heat values, it is always Q is directly proportional to the delta S and the constant temperatures. So that the Q value is we simply considered the entropy values, and finally the difference of the but high pressure and high temperature and low temperature sides, produce the difference value as the same, so that it is very clear the what exactly were discussed, the refrigerator, this COP of the refrigerator. This based on the expression, we get the same expression from these heat values. So that the COP is low temperature, that is T2 by T1 minus of T2. And the refrigeration systems are several types of refrigeration systems also there. Mainly air refrigeration system, ice refrigeration system, and carbon dioxide as one of the refrigerator, that is the CO2 refrigeration system, and vapor compression refrigeration systems, and vapor absorption refrigeration systems, and steam ejector or simply steam refrigeration systems, and some of the non renewable source of energy by using this Joule Thomson coefficient and all the things, the with the Petlier effect, that is a different case. But what is the importance of vapor compression refrigeration system? Before the vapor compression refrigeration system, nowadays all the refrigeration operations, mainly the domestic or industrial operations, the vapor compression as a refrigeration system, it is very considerable cooling, produce the very considerable cooling effect as compared to the air refrigeration system or ice refrigeration system. In the main advantage of the vapor compression system, it the as the air compression system or air ice refrigeration system, it requires more amount of the refrigeration, but the cooling media. But in case of the vapor compression system, it is use the but less amount of the cooling media like air or different types of refrigerants also there. That is R134A or R122 or R600 or R600A. That is several different types of refrigerants also there. They are directly were used in the vapor compression system. The vapor compression refrigeration systems are a closed cycle. It is works in the closed system. And in case of air refrigeration system, it is the open system, open refrigeration system. So as the refrigeration effect point of view, vapor compression refrigeration system, it produces the more cooling effect at the same consumption of the energy, same consumption of the energy. In this vapor compression refrigeration system, it is mainly the domestic refrigerators, And the main components of the vapor compression refrigeration systems, the compressor, condenser, and expansion devices and the evaporators. And broadly, were divided into the high pressure side and low pressure side of the devices. And how we are divide all the things. We discuss based on the things. The evaporator and compressor out inlet up to the compressor inlet where pressure locate the low pressure side, and at the outlet and condenser up to the condenser to the inlet and outlet of the condenser is where locate at high pressure side. The basic operation of the condenser, this is simply we observe the basic operation or basic principle of the refrigeration effect, how it is produced in the refrigeration, the vapor compression refrigeration. In this vapor compression refrigeration, we use as a vapor the R134A I use as the domestic refrigerator. At present, we use as the domestic refrigerators. That is, at the first we observe all the things we are discussed with the help of the what with the help of pH and TS diagram. In this one of up to this one up to the steam tables, we steam but so property of the steams, we are mainly focused on PV diagram and TS diagram. But in the case of refrigeration, one of the important chart, that is pH diagram, pressure and enthalpy. Pressure, as usual, we are taken into consideration is on the ordinate, and enthalpy is on the abscissa. That is, PV is on the y-axis and enthalpy is on the x-axis. Enthalpy is just simply the heat value. It is we consider just what we observe the things. The condition there are the condition one. This is the state one. That is, at the condition one, we simply think the theoretical vapor compression system. We simply consider some of the assumptions, that is the leaving condition of the refrigerant at point one, at the leaving condition of the evaporator, refrigerant leaving condition at the evaporator is saturated vapor condition. So that the point one is at the saturated vapor condition only. Just you observe, this is the saturated curve in the P theta diagram. That is up to the critical point. In the left hand side, it is the saturated liquid line, and the right side of the critical point or triple point, that is in the saturated vapor curve only. So that point one is indicates as per our assumptions, that is saturated vapor condition only. At saturated vapor refrigerant at low pressure and low temperature, that is at T1 value and P1 value, it is enters into the compressor. The compressor, we made one more, the assumption is the isentropic compression process. In this isentropic compression process, the pressure, but low pressure and low temperature of the vapor refrigerant is compressed, and it delivers and it increases the pressure and temperature limits up to the condenser level, or up to the maximum pressure and maximum temperature limits. So that that is the case. That is the case. This is the leaving condition of the compressor is point two. At point two, it is the superheated condition only. But this is after but superheated condition, it is enters into the condenser coil, where the condensation process is occurs at constant pressure process. So that in this condition, P2 is equal to P3. P2 is equal to P3. where in the compressor operation, what exactly we are would observe the things based on the enthalpy, how much of the energy is required to increase the pressure from P1 to P3 value, so that the enthalpy is increases from P2 minus of the sorry H2 minus of H1. That is difference of amount of the enthalpy value. It is the energy is required to run the compressor. That is we simply consideration of with work done in the refrigeration operation. So condensation operation is 2 to 3, but the compression operation it is not follows the isentropic process. That is S1 not is equal to S2. And at the same time, the one more important assumption is the leaving condition of the condenser is saturated liquid condition. What is the saturated liquid condition? Is saturated liquid condition is above the what below the point 3, that is the saturated point below the it is subcooling region, and it is the what the above the but left side of the saturated liquid line, that is saturated vapor saturated sorry in the wet region. So that the one more important consideration is the dryness fraction value is also very important one. So it is need not to be dryness fraction that is almost zero at this one, and then at point 3 only it is enters into the expansion device or throttling device, where the pressure and temperature is passed down from the point 3 to point 4. The point 3 to point 4, where exactly what happens, it follows the constant enthalpy operation, where H3 is equal to H4, where H3 is equal to H4. And then at the leaving condition of the evaporator, as we consider as same entry condition of the evaporator. So that low pressure and low temperature of the liquid refrigerant, it allows the in the evaporative coils, so that low pressure and low temperature of the refrigerant it is enters into the evaporator, and it extracts the heat from the substance, and the temperature of the substance it goes on decrease, and it absorbed by the temperature. How much of the temperature is given out by the substance is as equal to it is extracted by the refrigerant. That is the thing. It is the vapor liquid refrigerant is converted into the vapor refrigerant, and it is the delivery condition of discharge condition of the evaporator is at point 1. So the cycle is repeats. I think here what exactly we are mainly concentrate where the CO, how to where measure the COP of the refrigerator is in terms of the COP only. So COP is the refrigeration effect. The refrigeration effect is how much of the heat is extracted from substance, that is H1 minus of H4. That much of the heat value is absorbed by the refrigerant, or that much of the heat is lost by the substance. So that is we simply consider as the cooling effect or refrigeration effect. What exactly the work done is H2 minus H3, as in terms of the electrical energy, or some energy by using some energy meter, or whatever it case it may be. But in case of the heat values, H2 minus H1 is the total work done. Work is required to compress the fluid from the state 1 to condition 2. That is thing. So that the COP is, we define the COP like this. The quantity, the the expressions of all the things were mainly concentrate on only two, that is the evaporator and compressor. In the evaporator, H1 minus of H4, that much of the heat is carried by the cooling media or refrigeration effect, and H1 minus of H2 is that much of heat is required, or heat energy is the energy is required to compress the fluid from state 1 to state 2. This is the different types of that is only by consideration of some assumptions. The different vapor compression refrigeration systems also there. This always it is not possible. The refrigerant is leaving from the evaporator as a saturated vapor condition. It may be in superheated condition, or it may be in the in the wet region. If suppose in the wet region, what happens? So that in the wet, suppose the leaving condition of the evaporation in the wet region, ultimately we observe in the previous diagram, a theoretical diagram, the cooling effect is reduces, more or less the work required is same, so that the COP value is it is decreases. So by consideration of these conditions, what we conclude, we see next condition also there. Next one is also like that. The only thing. Uh, what we conclude that always the refrigerant from the evaporator, the leaving condition of the evaporator is always in the superheated condition is preferable condition, and it gives the more refrigeration effect, so that the performance of the refrigerator is also more as compared to the theoretical condition, or like it is living condition in the wet region, so that where more concentrate the leaving condition of the evaporator is hmm, leaving condition of the evaporator is in the superheated condition. The energy is required is more or less is same. But apart from all the things, it is also important. It is also important. One more consideration. One of the COP is affecting on suction pressure and pressure and discharge pressure. How the suction pressure is discharged? The suction pressure, it is in the theoretical condition. What this is the what continuous the continuous operation, that is 4 to 1. That is the theoretical condition. But in actual practice, the refrigerant is always enters below the theoretical point, theoretical value, that is at the P4 dash. Always P4 dash is the lesser value as compared to the P4 value. So that this much of the pressure is difference is occurs in actual condition. What we observe with the theoretical one, and the effect of the suction pressure. Whenever the suction pressure is less than the theoretical one, so that what happens is here, the amount of the cooling effect is reduces. That is H1 minus of H1 dash amount of the refrigeration effect is reduces. And just simultaneously you observe work done. The work done is increases the value of H2 dash minus of H2 value, so that here what we what we understood that the energy required, or the energy is required the energy is required is small, and cooling effect is falls down some amount of the cooling effect. By simple consideration, what we conclude that the pressure is decreases, and the specific the volume of the vapor is increases, the work done is also increases, that is the amount of the work done is H2 minus of H2 dash minus of H2, and the refrigeration effect is reduces, that is H2 H1 minus of H1 dash, and ultimately the refrigeration effect is by the consideration of the effect of suction pressure. This is the work done, the refrigeration effect H1 dash minus of H4 dash by H2 dash minus of H1. So that with this simple expression, we conclude that it is the COP value is reduces and work done is increases, refrigeration effect is reduces. So it is somewhat considerable the parameter, the suction pressure. And coming to the effect on the effect of the discharge pressure, the effect of the discharge pressure, the based on the what the after number of cycles, it is not the discharge, it is not leaves the refrigerant at point 2 of the compressor, that is the discharge condition, that is point 2. It is above the line, it is above the line, it is above the line, above the line. So that what we conclude that the refrigeration, the work required is improves, and then refrigeration of the from H2 dash to it is the condensation process. The what it leaves the condition is the H3 dash. What we observe in the throttling process, finally in the refrigeration effect, what we observe is that the refrigeration effect is reduces from H4 dash minus of H4. That much of heat, the refrigeration effect is reduces, and H2 dash minus of H2 value is what the work is required to run the compressor, that is that much of the value is we required. So that what finally we conclude the value, the refrigeration effect to the work done, refrigeration effect is H dash minus of H4 dash, and the work done is H2 dash minus of H1. So that by simple consideration, in this case also the refrigeration effect is reduces and work done is improves, so that the COP or coefficient of performance of the refrigerator is reduces. So that with this lecture we try to continue in the next class.